root of x squared. Isn't that like a number over infinity?
But it's we're letting x go to infinity, right? So isn't that infinity on top? And then infinity squared plus 1 is infinity?
Yeah.
Square root of infinity is still infinity. So you have infinity over infinity, which is, we don't know, right? Infinity over infinity is like 0 over 0. We don't know what it is. So what I'm doing right now, please don't lose sight of this, I'm just focusing my attention on that red piece. And I'm going to do that like scratch work on the side, and I'm going to see if I can figure out what that limit is. So I'm taking the limit as x goes to infinity of x over the square root of x squared plus 1. And I already said that's infinity over infinity, so I'm going to use L'Hopital here. Do you see why I was saying my instinct earlier was to do something else? I could kind of see that this was coming. All right, 1 over what? 1 over 2 square root of x squared plus 1 times 2x. And the 2's cancel. And where are we going to be? Almost the same thing. It's going to be the reciprocal, right? When you do that, you get x over this, and then when you flip it, you get that one flipped over, which means we're going to be stuck in a loop here, aren't we? Yeah. We're going to be stuck in a loop. So I have no choice but to go to the other method, which is to come in here with 1 over and 1 over. What am I going to come in with?
1x.
1 over x. 1 over x. Because when this goes into the root, it gets squared. Okay, so we're going back to like stuff we did a long, well, summer class, so it wasn't that long ago. But I'm going to go here, and I'm not doing L'Hopital, right? I'm going to go this, x goes to infinity. Okay, this becomes 1. And then when I push this in, it becomes a 1 over x squared, and then it distributes through to both of these. So I get 1 plus 1 over x squared. And that goes to what?
0.
This goes to 0, plus 1, 1, square root of 1, 1 over 1. So that goes to 1. And that means this thing went to 1, right? So we have infinity over 1, which goes to infinity. Boy, they threw that one at us. Curveball there. Okay. All right. So, recap. We have another hour and 20 minutes. So if we have 0 over 0 or infinity, go straight to L'Hopital. This problem, we had infinity minus infinity. I couldn't factor, so I did a conjugate, right? And then the conjugate kind of got messy, and when I did some work on the side, was like L'Hopital wasn't really helping, so I went back to the old school method. I got an answer. All right, we're now going to really shift gears and look at a type of limit that we have never looked at before, all right? Yeah, here it is. Do you remember that sheet I gave y'all that had the 4 boxes on it? Yes? You have, in the 4 boxes, that sheet that I gave you have those 4 boxes. And in the top left, there were these different forms that we had. They were 0 over 0, infinity over infinity, right? What else? 0 times infinity, infinity minus infinity, 1 to the infinity, 0 to the 0, infinity to the 0. That's it, right? That's what's inside that box. All of these, when you take a limit and you get any of these are called indeterminate forms. We have already talked about these. 0 over 0, we know what to do here. Algebra or trick, but now we have L'Hopital, right? Infinity over infinity, algebra or trick, but now we have L'Hopital, right? Infinity minus infinity, we kind of know what to do with that. We try and factor maybe a conjugate. So we're kind of iffy on that, but we have some techniques, right? We have not at all looked at this, or this, or this, or this. We still have to cover all of those, and we're going to do that all right now in the next hour and 20 minutes, all right? We are going to look at all those different scenarios. And I will tell you, in order to do these three, you have to be able to do this one. So this is going to be very important that we understand how to do this. So let me give you an example first. Limit x goes to 0 from the right of x times the natural log of x. And this right here, this can be plus or minus infinity. Okay, it doesn't matter. That one right there. Let's think about what's happening here. As x gets really small, right, goes to 0, where does this one go? 0, right? This goes to 0. Now, am I telling you that that number is 0? No, I'm just telling you that it's getting really, really small, right? So you have this tiny, tiny number, 0.0000001 or something, right? You got this tiny number, and then you're multiplying it times natural log of 0. But see, you can't plug 0 into natural log, can you? But we can approach 0 from the right. What does the natural log function look like as you approach 0 from the right? It heads down like that. Yeah, we have that asymptote, right? So where does the natural log function go as we head to 0 from the right? Negative infinity. So you see that this is headed to negative infinity. So what happens when you have this infinitesimally small number times this huge negative number? You don't know who wins, right? Like, how small is this? How big is this, right? You don't, it's like having 0 over 0 or infinity over infinity or infinity minus infinity. It's like this battle that you are inconclusive about. You just don't know what the answer is. What you don't want to say is that anytime you have this, the answer is 0. That means you don't understand what's going on. Because this is not the number 0, it's a tiny number. This is not the number infinity, it's a huge number, right? You understand that we have like this indeterminate thing? So we've got this form. How do we attack this form? How do we do it? Y'all ready to see? Okay, the trick on this one is that you have to have two things being multiplied to get this, right? What we're going to do is we are going to rewrite this. I'm going to rewrite it. Just algebraically, I'm going to rewrite it. But I'm going to rewrite it in a way that's going to give me one of those two forms. Okay, watch me do it first. I'm not doing any L'Hopital. This is just purely algebra. I'm going to rewrite this like this. Do you agree that that's the same thing?
Yes.
Yes?
You just moved the x.
Y'all see what I did? All I did was I took that x and I dropped it to the denominator. But to drop it meant that I had to write as 1 over x. Because if you wanted to go and put that x back, you could flip it back up and it would come back like this, right? So that's just purely algebra. Yes?
Could you have just put a negative one?
X to the negative 1?
Yeah.
I could have, yes, and it would mean exactly the same thing. But I'm doing it this way because now I want you to look at it from a different perspective, all right? So everyone's good with that? That's just algebra? I would like for you to now let x go to 0. Where does this go? We already said where this went. Where does natural log of x go to as you approach 0 from the right? Negative infinity. Okay, over. Now, this is the one. Where does that go? 1 over, where are you headed? 0 from the right, yes? So your numerator is what? Fixed, and your denominator is smaller and smaller, and always positive, isn't it? Because you're approaching from the right. What happens if you have a fixed numerator and your denominator gets really small? Your denominator gets small, but your numerator stays fixed. That ratio becomes, think about the number 1 and divided by a small number. 1 divided by 1/10 would be? It gets large, right? 1 divided by 1/10 is 10. 1 divided by 1/100th is 100, right? So you have fixed over something that gets small, that ratio gets huge. So what's in blue here goes to infinity, right? Do you want to see how I did that? Now do we have infinity over infinity? Now can we use L'Hopital? Yes. That's the trick. When you see 0 times infinity, what you're going to do is choose one of these and drop it down to the bottom, all right? Drop it down meaning put 1 over it on the bottom. And now use your L'Hopital. Okay, here comes L'Hopital. So by L'Hopital's rule, I have limit, x is approaching 0 from the right. Okay, what's the derivative of the top? 1 over x. Right? Isn't that the derivative of natural log of x, 1 over x? Right? We did that last class? Right? 1 over x. Now, what's the derivative of 1 over x? I did that on the side just a second ago. What did we say? Remember, I put it right here. I said, if you take derivative, 1 over x, right? What did it come out to be? Negative 1 over x squared, right? That's what that was? And now, before you do any more L'Hopital, clean it up algebraically. You can flip this up, can't you? Okay? And you get limit x approaches 0 from the right. It'll be, I'll do it slow, 1 over x times, flip it up, x squared over negative 1. That's the limit as x goes to 0 from the right. That's the same as negative x. Right? These x's, one of them cancels. You still have a negative 1 there. So you get negative x. And what's that? If x goes to 0, what's that? 0. Your answer is 0. On an exam, on your next exam, if I give you a problem like this, and you give me this correct answer, but your work makes no sense, you're not going to get credit, okay? You have to show me how you're deducing that that answer is 0, right? This happens a lot with these problems. Students will get the right answer, but what they did makes absolutely no sense, and they just got kind of lucky, right? So just be forewarned. I'm not looking for correct answers. I'm looking for correct procedure. All right, let's just run through it one more time. We had 0 times negative infinity. When we have that, we've got to pick one and drop it down to the bottom, right? And then we should get then either infinity over infinity or 0 over 0. And then we do L'Hopital. Now, I want to do the same problem over again. I dropped the x, didn't I? There's nothing that says that I couldn't have dropped the natural log. See, I have two things being multiplied. It's your choice which one to drop. So we still have 0 times negative infinity here, right? Let me drop the natural log down this time. And I want you to see the difference between the two methods. If I drop the natural log, it has to be 1 over natural log x. What's that?
So the bottom would have, oh, so
What? Yeah, 1 over natural log would flip up and it would just become that, right? Okay, what happens as x goes to 0? That goes to 0, right? X is just 0. X is going to 0, so x is going to 0, right? All right, you have to be extremely careful on this one. Where did we say natural log of x was going when you went to 0? Negative infinity. So you now have a fixed number over something that's becoming infinite. Not small, but infinite. What happens to that? It goes to 0. So this whole bottom right here goes to 0. And now you have 0 over 0, right? And you can use L'Hopital. Do y'all see what I'm doing? So let's try L'Hopital, and you're going to see this is going to suck here in just a second. Limit x goes to 0 from the right. The derivative of the top is clean, right? What's derivative of x? 1. But the bottom is not clean because it's a quotient. That's 1 over natural log of x, right? Not just natural log, it's 1 over natural log. So how do you take derivative of 1 over natural log?
1 over 1.
You have to make a decision how you want to do it. If I say take derivative of 1 over natural log x, you can either do the quotient rule, right? Do the quotient rule, or if you don't want to do the quotient rule, you'd have to rewrite it like this. Natural log of x, all of it to the negative 1, and then take the derivative. So if you wanted to bring that natural log of x up, you'd have to write it that way. And you'd still have chain rule. You still have to bring the negative 1 out, all of this to the negative 2, times derivative of what's inside. It's messy. And so is the quotient rule. It's messy. So even though you have the freedom to choose which one you're going to drop, usually one way is better than the other. And in this case, dropping the x is definitely better than dropping the natural log. Do y'all see that? The most common mistake I'll see students make is on this next line, they'll write this. And it's completely wrong. All they did is what? I don't even know what they did. They left the 1 alone, they just took the derivative of natural log and put it underneath. That's completely wrong. Because this is a quotient and you're taking derivative of the whole thing. So I'm going to stop here because I don't even feel like doing that. I already got the answer. I was happy with the way we did it. All right.
Do you know, like, a trick to know which one is better to use, or is it easy to just
Do I know a trick? I just think about it. Like here, I think about what would I rather see in the denominator? Would I rather see a 1 over x or a 1 over natural log? Well, 1 over x, I know that derivative, right? 1 over x I know because my professor told me once to remember what derivative of 1 over x was. You know, but 1 over natural log is just a little more involved. I'm not saying this can't be done. I'm just saying this is not as nice. I think we need to do another one. Natural log x times tangent x. X is headed to 0 from the right. Where's this one headed? Negative infinity. How do you know that? We just did that, right? We just did that, right? This headed to negative infinity. All right, where does tangent go as you approach? Well, if you plug 0 into tangent, what's tangent of 0? 0. So you have negative infinity times 0, right? That is an indeterminate form. It's this. Okay, so don't tell me the answer here is 0, right? Because it's not. You've got to figure out what it is. Maybe it is 0. Maybe it is. But not by just looking at that. So I've got to drop 1 down. I don't think you have a good option here, right? You have what? You going to do tangent? Yeah. Drop the tangent? Yeah, I'm okay with that. So let's rewrite it, right? This is not L'Hopital. This is just me rewriting it. I'm going to leave the natural log on top. Another reason I like the natural log on top is because that derivative is just 1 over x, right? So that's very clean. If I drop tangent to the bottom, what does it become? 1 over tangent? So I could write cotangent, couldn't I? On the bottom instead of 1 over tangent? Could I? What do y'all want to do? 1 over tangent or cotangent? Totally up to you. Cotangent? Let's do cotangent of x. Now, you can check for yourself. I mean, this is still going to give us a problem. This is headed to negative infinity. And if you go look at the cotangent function on I think your reference sheets have it. If you look what's happening as you approach 0 from the right, where is it headed? Does it have cotangent on there? It's on your trig. Right, flip over one more. Right here. Do you see cotangent there?
Yes.
If you look at the cotangent graph, it looks like this. And at 0, here's 0. From the right, where's it headed? Infinity. So you do get infinity over infinity here. Right, so you can use L'Hopital. We still have an hour. Cranking away. Limit x goes to 0. Oh, L'Hopital, so I need to put my little L there from the right. Derivative of top, 1 over x. Super happy about that. All right, what's the derivative of cotangent x? Negative cosecant squared x. Negative cosecant squared x. Whoa. Right? Whoa. I'm going to clean some stuff up here, right? This is limit x approaches 0 from the right. Okay. That's the same as negative 1 over sine squared x. Right? Isn't cosecant just 1 over sine? That's what cosecant is, right? 1 over sine. So I can replace this with 1 over sine squared and then just bring that negative up on top. Y'all buy that? Can I rewrite it this way? Was there a question? No? Okay. Can I rewrite it this way? Bring this up like that. That all right? Still just algebra? Now what? What do you get if you try and plug 0 in? What's sine of 0? Sine of 0? Are the wheels coming off? Y'all okay? Sine of 0? Y'all are thinking cosine 0. Sine of 0? 0. Right? Sine's the y coordinate. What's the y coordinate on the unit circle at the angle of 0? That's just a brain fart. Y'all are going to be okay. Sine of 0 is 0, right? 0 squared, 0, negative 0, 0. Top is 0, right? Bottom is? 0. You have 0 of 0. So what can I do? L'Hopital again. L'Hopital. Limit. X goes to 0 from the right. Okay, derivative of top and bottom. What's derivative of the top? Well, chain rule, right? So negative 2 sine x times cosine x all over, this is the great part, 1. So I brought out the 2, right? Brought out the 2, this to the first power, and then times derivative of sine, which is cosine. And then I do derivative of bottom separately. And now I'm happy, because I no longer am going to have 0 over 0 or infinity over infinity. What does the top go to? 0. Yeah, negative 2 times 0 times 1, right? Negative 2 times 0 times 1. So you get 0 on top, and on the bottom you have 1. That's not a problem. That's just 0. So see, your answer was 0, but you had to work for it. All right, y'all hanging in? I wish I could just give you a bunch of problems you could practice, but we've got to get through these 3. Okay? We've got to get through these 3. All right, so the idea again, last time, if you see 0 times infinity, you're going to take one of them and drop it, right? And then you're going to go use L'Hopital. Limit. X approaches 0 from the right of x raised to the sine x. X raised to the sine x. Let's just see what's happening. If x goes to 0, what does the base of this want to become? 0. So this is headed to 0. Raised to what power? Sine of 0 is 0, right? 0 to the 0. Look, I need you to just take a breath here for a moment and understand why that is an indeterminate form. Okay, we need to understand why this is something we don't know the answer to. First, let's think about the base. This number here, am I saying that it is 0? No, I'm saying it is getting closer to 0, right? So the base is sitting there, and the base is like, hey, I'm trying to get really, really small, right? And the exponent is headed where? To 0 as well, right? But we've learned that in algebra that if you take anything and raise it to the 0, shouldn't you get 1? Yeah. But we also know that 0 raised to any power should be 0, right? So we have this conflicting thing happening here. It's like the base is like, I want to be 0. And the exponent's like, but I want to turn you into a 1. Does that make sense? They're at odds with one another. And so that's what makes this an indeterminate form. Let me just show you a quick example of something that would not be an indeterminate form, something that would look very similar to that. What if you had, on the bottom, x plus 1 to the sine x. Now what's happening?
0 plus 1.
0 plus 1. So the base is trying to become a what? 1, and the top's trying to become a 0. And in this case, they're actually helping each other out, right? It's like the base is like, hey, I'm trying to get to 1, and the exponent's like, hey, that's what I do. I turn things into 1. Does that make sense? Okay, so this is not an indeterminate form. The answer here would be 1. You'll see the difference? All right. So what do you do in this case? We haven't seen this case. And this is going to be for all 3 of these cases, right? For all 3 of these cases, we do the exact same thing. You ready? Yes?
Take the natural logarithm and take the e to the power of that natural logarithm.
There's 2 ways to do this that are normally taught. That's one. And then there's another way. I'm going to show the other way. That's the way I normally do it. But the way you mentioned is yes. That is one way to do it. All right, so here's what I teach. This is normally taught one of 2 ways. So when you have one of these 3, okay, when you have one of these 3, what I'm going to do, what we're going to do, unless you've learned a different way, you can stick with that. I am going to call this limit y. Okay, I'm going to come in here and I'm going to say, hey, everyone, whatever this limit is, whatever it is, I'm going to call it y. Right? Anyone have a problem with that? So I want to know what y is. At the end of this all, I want to know what y is. Right? Now what I'm going to do is I'm going to bring in the natural log on both sides of this equation. So I'm going to take the natural log of y over here. Over here, I'm going to take the natural log, but there's a property of limits that says that when you do the natural log, you can pass the natural log past the limit. And so it becomes this. Okay? So I did natural log on both sides, and then passed the natural log through the limit to be right in front of the x. So I'm doing natural log of x to the sine x. That okay? Next step. Natural log y equals, and this is the big, big step. This is the reason why we brought the natural log in, because of this next step. I am now going to bring the sine x out in front of the natural log. Now that is a property of logarithms from college algebra, and we talked about it last class, that if you have a power, right, it was this property right here. If you have natural log of x to a power, that power can come out and you can have n natural log x like that. This power drops, right, in front of the natural log. That's exactly what I'm doing. I have natural log of x to a power, and I'm bringing the power out in front, just like that. You all right with that? Okay. Take the limit. What are you seeing?
1.
What's this become?
0.
0. What's that become as you approach 0 from the right? Negative infinity. Does this look familiar?
0 plus
You now have this, don't you? That's the whole point of us bringing the natural log in. Is that what used to be what? Well, hold on. It was 0 to the 0, right? We have somehow transformed this into 0 to the negative infinity. Let's just talk after class. Do you have a minute after class? Okay. All right.
drop this side.
So this is the whole reason I said let's understand this, is because when we do these, we bring a natural log in, we pop it out front, and we are guaranteed to turn it into this now. And now if you know how to do this, then we just follow through. Okay? So I'm going to drop one down. Which one do you want me to drop? Sine. Let's keep the natural log on top. Okay, notice I'm going to keep my natural log y equal this whole time. I'm going to leave the natural log of x there. And on the bottom, I have to write 1 over sine, right? Not sine x, 1 over sine x, right? I could also do cosecant. I think I will do cosecant. Okay, so natural log x over cosecant x. Now, what happens when you let x go to 0 here? That goes to negative infinity, right? Cosecant, if you don't know what it does, look at your graph on your cheat sheets. What does cosecant do as you approach 0 from the right? Positive infinity. So now you have infinity over infinity, don't you? And now you can use L'Hopital. Finally, we've gotten it to L'Hopital, right? Yep, natural log of y is going to come this whole time. Keep writing it. It's like you're writing two sides of an equation, just the whole way down. So now we have, and I'm using L'Hopital, right? Because I'm doing that, I'm putting an L over the equals to let you know I'm about to do L'Hopital. So limit x goes to 0 from the right. Okay, derivative of the top is 1 over x. We're happy to see that. Derivative of cosecant of x is negative cosecant x cotangent x, right? Look off your formula sheet. Do you see it there?
Yes.
Yes? All right, I'm going to try and clean this up before I try and do anything else to this. Natural log y equals limit x approaches 0 from the right. Okay, I'm going to try and help you go through this a little bit slow here. This is going to be equals, over negative 1 over sine x. And then cotangent is cosine x over sine x. I'm just kind of peeling these apart. This is 1 over sine, and this is cosine over sine. And I'm doing that because I want to bring those up and flip them and put them upstairs with the 1 over x that's on top. What's my next line going to be? What's on top? I want to bring these up. I want to bring these up, like bring these and flip them like that.
Negative sign.
So you got negative sine, and then another sign, right? I could do sine squared, but I'm just going to leave it like that. And what's on the bottom? Cosine and x.
Negative.
I put the negative on top. Is that all right?